I will show you how to derive how to calculate, how to determine the capacitance for a cylindrical capacitor. This I got this figure from a LibreText. Yeah, very nice figure actually. This I didn't make. In general, I make my own figures. So first, before we start, everything here, right? I put like my reference frame here. I have two plates. The first thing that I have to do. So this is actually assume charges here. I'm considering that this outer cylinder here has a positive charge plus Q, and I'm considering. Sorry, it's the opposite. This is minus. This is negative charge outside, and I have a negative charge inside. Oh, man, that should be correct. This here, draw. This is positive charge plus Q. Cylinder. The outside is minus, but doesn't matter much. I'm considering my reference frame like this, and as you can see, because since we are going to use Gauss law to solve this, is important to remember the direction of the normal the normal area vectors, right? So we have here for the I'm considering this bottom, this top, and this lateral. I'm considering this is in the minus k hat, this the positive k hat direction. I'm representing the normal area, the area vectors as in green here. And since we know that for this cylindrical symmetry here, the electrical field is going to be radial. You know this when you solved the problems there in Gauss law. I'm not going to much too much effort now to explain it again. Okay, so this is the first one. The second thing that I have to do is actually apply Gauss law to this particular geometry here. Right, as you can see, you can write all these integrals here. This is the bottom, the top, and the lateral. We should put this one here. Surfaces, but since the electrical field and the area vector are parallel, sorry, they're not parallel, they are perpendicular. This is going to be 0. Right, this is what is written here. We learned this already in okay, so you just have to worry about this integral here, and if you solve, let's solve this integral. This is the electric field is constant. In this case, I'm going to have the electrical field by the area. Right, my Gaussian right there is in orange here. There are cylindrical Gaussian surface. The red is exactly the same. Here doesn't change. So this is the area, the lateral area of this cylinder, guys. Like we did, this lateral area here is going to be 2 pi r. Times the radius, Gaussian, the surface represents Gaussian surface, and times L, length of the cylinder, and everything is going to be close to small q divided by, we can electric here, what we will electric field, this is going to 0 L Q R fraction represented by R hat. Okay, this is now for the next step. I'm going to use the electric field to calculate the potential. We know how to calculate, we just have to integrate integral here, going to be minus size here, and so outside of the, this is going to be radius R1, and the scalar product R hat and SM integration is going to be in the radial direction, R hat as well, scalar product since the unit vectors are parallel. We can solve this we know actually this one is going to be the natural logarithm, right? So what I have here, that actually this potential, substituting all these values, you can find that the potential for kind of particular geometry is going to be, again, one constant here multiplied by this okay, let's almost there, dudes, almost there, almost there. And again, the last step is actually just to calculate it. That's the easiest one since we have the expression, right? we can actually calculate this. Okay, you just have to substitute here to find the capacitance. And if we do, want to finish this before this class is over, because very interesting result as well. We are going to realize something very important here. So if you just substitute, right, this the last two equations, the last equation that we did, right, for the voltage here, what we are going to find is actually that the capacitance for a cylindrical capacitor is going to be what people keep meaning 2 pi epsilon 0 L divided by the natural logarithm of know. And what is the significance of this result? Well, first of all, as you can see again, the capacitance of this new capacitor also depends on the geometry, and explicitly speaking, it depends on the length, right, L, and the ratio here between the two radius, the R1 and R2. This is very interesting. I'm sensing a kind of pattern here actually. As you, we're not going to have time to finish today, I guess. But if I could, but let's rewrite here. Rewrite this just for fun, and let's write this as C equals epsilon 0. Then you have all this geometrical metric vector here. Pi now divided by logarithm 2 divided by 1. Arranging, and you can clearly see that actually we have again here like previous, so to have like epsilon 0 and multiply by some kind of geometric factor, the same. Do you have questions until now, guys? Any questions? I'm gonna put here this the color and actually identify some kind of pattern for this kind of problem. We are very interested in physics, right? Physics find patterns for everything. Questions? No. So let's see. You have 9 minutes. Now let me go to the next one. Let me just put in here. Remove the lines. Actually, see better. Not so much visual pollution.